Okay, so we were saying, how do we apply everything we have seen to the crowdfunding case? Like, you want to allow people to donate to your project, and only if they donate enough money above the funding goal, you get the money. Otherwise, everybody gets reimbursed because you don't have enough money to do anything reasonable. Okay, so the way you would do it is, so you would create a smart contract with an associated application account. The first the way you create it is actually by making an application call to create a smart contract. And the smart contract will be stored in this global state, the start date, the end date of the funding goal, how much funding is currently received. So at the beginning, 0, but hopefully at the end, more than the fund goal. And the receiver address, who will receive the money at the end of the day if the funding is successful. Then donator can come and make an atomic group of 2 transactions. One transaction is sending money to the application account, and the other transaction is to say, hello, opt-in and update my local state, so it includes the amount I gave. So this way, so everybody can come, and at some point, when this happens, the smart contract will update the local state of the user to register how much, to record how much they gave, and they would also increase the current funding received. Now, at the end, after the fund end date, if the current funding received is higher than the fund goal, the project creator, like the receiver address of the fund, can call the smart contract and get back all the money that has been raised by the crowdfunding. And this is done using an inner transaction done through the application app. On the opposite, if the current funding is not enough, everybody that donated to the project should come and request to be reimbursed. So this is essentially the same thing as the first case, except that in the first case, it's a project creator that makes the transaction and is the only one, and he gets all the money. And in the second case, if the current funding is not sufficient, then everybody needs to come to get reimbursed. That's very, yes. Exactly. So each individual person would be responsible for their own reimbursement. And this is in general not really it's a limitation in general of all the blockchain, because you cannot really, suppose that you have like 1 million persons that's crowdfunded. You don't want that the smart contract does a loop over 1 million person. It would be like on Ethereum, you cannot imagine the gas you would pay, and on Algorand, it's just not allowed, full stop. Like it would cost too much processing to the blockchain. So everybody needs to come and get reimbursed and pay a little bit of fee to process this. Yes. Sorry, can you repeat? Every time you do an application transaction call for this application, it runs the logic. But if there are 2 applications, yes, I create an application, you create an application. If you make an application call to my application logic is run. But your application logic, it stays, nobody read it or look at it. Yeah. Yes. Every time you do an application call, it runs a smart contract code. Yes. Yes. Okay, so there are cases where your incentive to want to donate is just because you really like the cause. Like some person like has a very interesting story, they need money for college and they really believe in them. Yeah, and some crowdfunding platform, they also have like some gift, not gift, I mean something they give back. Like if the project is successful, you will receive like a small prototype or actual project. The actual project is an actual object or actual thing that you will get. You never have like any guarantee. And the blockchain cannot guarantee that you will get back what they said, like, because there is no way for the blockchain to verify. So you could, in theory, what you could do is you could have like some independent set of jury or mediator that would check that the project like delivered according to what they promised, and maybe unlock progressively the money if the project satisfies a milestone, something like this. Like you could imagine such more advanced system where there is like the project needs to deliver something to the people who donated, and like there is some independent bench of people that verify that the delivery match, and like the project does not receive immediately all the funds, but they receive only when as delivery increase. So you can do more advanced things, yeah. But there are cases where it's really just you really like the cause, like so you want to help someone. I think somebody else wanted to ask a question. Yes. Yeah, so the stay in the application account. Now you can say, you can add in the smart contract a clause that if after 10 years nobody claims them, then the creator of the project receives them or whatever. So it's up to you to decide what. But if you don't do anything like this, then the token are just like frozen there. You could also say that anybody can claim on behalf of anyone. Like, and you can also say the fee is paid through the reimbursement. So actually you could have that anyone can actually trigger the smart contract to reimburse anyone. You could, so there are many ways you can design the smart contract to do that. Okay. So up to now it was, yes. Okay, so that's the $1 million question. So if you have all your time in your life, you read the smart contract, you scratch your head a lot, and you check that it does what it claims to be doing. And even if you are very smart, sometimes you will miss things. And if you are a layperson, I think it's like any product, like why do you think your car will approximately do what it will need to do and not do anything dangerous? Like the things that is worse in crypto is in the blockchain world, there are two things that makes it way worse than that. Is that one, there is no regulation. So like at least when you buy a car, there is somewhat like a regulator that you are sure to get something somewhat safe, and you don't need to inspect every part of the car that they did it properly because there is somebody verifying some. But there is nothing like this in crypto. Like in crypto, in the crypto world, like anybody can do anything, and it's just a question of trust. There is no regulator. And then the second part that makes it worse is that in the real world, you have like a judge and you have like a justice system. So if you buy something that is defective or you lose money by a scam, you can go sue someone, and sometimes you get back your money because the money is never like completely locked, or it's like you can kind of stop movement of money. The justice system has some power. But in the case of blockchain, you give money to a scam project, and the scam project actually, they pretended it was a crowdfunding, but actually all the money went directly to the owner, and there was no recourse. I mean, there is no recourse at the end of the day. Like maybe you can try to sue, but the person is not necessarily in your country, and you don't even know who the person is. So that's very, very difficult question. You wanted to ask a question? Oh, I see. And the point is, even if you are very good, like you can make mistakes, and I will never be able to read all the smart contracts that I want to use, maybe. So it's very, very difficult question. Okay, so so up to now it was very, very high level. I talked to you, program, access, blah, blah, blah. There was no like actual line of code. So now let's go deep and see what things look like. Okay, so little bit more detail about how smart contracts work on Algorand. So the transaction first. Transaction is not just a basic transaction like call the application. It contains some additional information. Application array, account array, etc., argument array. So let me not talk too much about these three, but they are used for some purpose. This one is more important, the argument array. It indicates what kind of method you want to execute on smart contract. I want to withdraw my money. I want to withdraw this amount of money, anything like this. So that this argument array, that's where you indicate this kind of thing. On the other side, the smart contract side, so the way it works is that we said that we see it's a stack-based system. I will show you how it looks like. And it has access to the global and local state that I talked to you about. It has access to something called a temporary scratch, like something where you can put temporary variable. It has access to the transaction property, so that you have seen that smart contract can access the properties of the other transaction in the group. It can say, okay, I got paid this amount. And it has access to some global variable. So let's go a little bit deeper. So I told you the smart contract is written in TEAL. TEAL is a stack-based language. So I will tell you what a stack-based language. At the end of the day, for your homework, you will write in Python. So you can just scratch this and say, okay, I don't care about this detail. It's not interesting. I would still recommend you to follow this in detail for two reasons. One reason is that if you want to do any advanced CS, you will need to learn how to do VM, like JVM, like things that execute your code. Like you need to understand what's happening deep down. And stack-based is one of the ways to do VM that is extremely important. Like the other one is registered. So this is something that is very important to you to understand because it's something that is useful in your CS career if you want to do anything a bit advanced. Then, yeah, so that's one reason. The second reason is that if you write a smart contract and it does not work, unfortunately, the debugger only shows you the TEAL and the stack-based thing. So you better need to understand what's happening. Otherwise, debugging it is a bit of like shooting an arrow in the dark. So it's better to understand it a bit. Second thing to know, it's Turing complete for those who know. So if the memory was infinite, that's very important. The first thing is that the only thing a smart contract at the end does is return true, I accept the transaction, or false, I reject. So you can do many things in the middle, many effects, but at the end, it's return true or false. It approve or reject. Smart contract Algorand manipulate two types, the uint64, so unsigned int 64, like 64-bit of unsigned int, and byte arrays of up to, I don't remember which size. There is also support for 512-bit integer written as byte array. So very simple language, there are only two types. Like usually, if you think about language that we use, usually there is like int, unsigned int, floats, double, like byte array, structure, map, very complex. There are only two types. And finally, usually you don't write in TEAL, you write in a higher language, which is PyTEAL, which is converted to TEAL. Okay, so what's stack-based language? So let's look first at the stack. So I hope that all of you know what a stack is. So you can push people on the top. I mean, not people, elements, and you can pop on the top. So you can always add on the top or remove the top. That's what a stack is in computer science. Okay, and why it's stack-based is because essentially the program is in two parts. There is a part which is like the code of the program, and you have a stack. And the way it's executed is that you start here, you execute the first instruction of the program, and say int5. Int5 means push the integer 5 to the stack. So you put it on the top of the stack. Then int 1000, push the integer 1000 on top of the stack. Then larger or equal. So this is a special operation. I mean, this is another operation. So each of these things like int, larger or equal are called opcode. And larger or equal is an opcode that pop out the two last elements of the stack, 1005, compare them, and push on top of the stack the result of the comparison. So here it's false, so it pushes 0 because there is no boolean in TEAL. It's false is 0, true is 1. And if you look at the documentation, it says this is an opcode. It pops A and B, and it pushes a value uint64 such that if A is greater than or equal to B, then it's 1 for true and 0 for false. So that's how the language works at the core of it. Like you have the code, the stack, and the code is executed naively like this, and it manipulates the stack. It's a bit of like a stack automata if you have seen this kind of thing. Okay. Okay. Wait, why on earth is it? Okay, not something wrong happened. That's okay. So let's look at other opcodes that are very useful. So remember, one of the first things you want to do is accessing the state. Let's start with the global state. We have an opcode which is app global gate. And this opcode will take the stack, pop the last element, read it, interpret it as a key to look in the database of the local global state, and push back on the stack the value. So let's see it on an example. Suppose that you wrote byte tally void byte tally vote yes followed by application global get. So at the beginning, at this point in time, there is on the top of the stack tally vote yes, the byte, right? Tally vote yes. And what the opcode app global get will do is that it will pop out the top, go to the state of the data of the blockchain and the state of the application, get the key tally vote yes, get the associated value, and then push on top of the stack the associated value. This clear? Okay. And then you can do the similar thing with putting value, with different value. Now you can also store value. I just show you because I will show you in the example, in the demo example, so I need to show you this. You can also store value to the temporary scratch space. So store I will pop out the last value in the stack and store it in the temporary space I. It can be any number between 0 and 255. And load is pop out nothing and just pushes the value that was stored at I before on top of the stack. Okay, so let's do a bit of a demo. So this is my code. Wait, is it big enough? So this is my code. Is it visible? No. Oh. Okay. Okay. So the code looks like this. So forget about that right now. So then it reads it push counter and it reads the global variable counter. Then it push one on the stack, add it, store the result of the incremented value. We'll see in an example I go slightly fast and then we'll see slower. And then it stores essentially back in the counter. So essentially every time you call this application, it increments its global state counter. Okay. So wait. Yes, you can think of them as register. Yes. Yes, 256. Yeah. So I think I need to increase this thing too. Okay. So the first thing I need to do is I need to send the creation transaction that will send to the blockchain, like the transaction. I mean, this script is sending to a blockchain a transaction that creates the smart contract on the chain, that deploys the smart contract on the chain. And at the end of the deployment, I get my application ID. So this smart contract got the application ID 33. That's now as it will be. And its associated app address is this value. Here we don't care about the app address. It's so basic smart contract. So now let's see what the global state look like. Actually, the global state is empty. We did not execute the smart contract. I mean, we execute the creation, we did nothing. Now, let's execute the smart contract. So this script actually calls the smart contract and execute it. So So you see that on Algorand here, everything is real time. And you see that it takes about 5 seconds for a transaction to happen, because on Algorand, transaction takes 5 seconds to be finalized. That's why you see 5 seconds. So let me call it twice. It will increase the counter twice. And now I can check again the global state. And I see, okay, so you can ignore the TP, but the UI is the value of the global state counter, and it's 2. And if I call a third time, it would just like become 3. So every time I call, I make a new transaction to my blockchain, and that calls the smart contract that updates the global state. So let's see now how you debug this. So you can see now it's 3. So let's suppose that I don't know what exactly is happening, and I want to understand what my smart contract is doing. I have a debugger that I run. Okay. So now you see, okay, so now I really need to increase, I guess. Wait, how do I zoom in here? Okay, so my debugger allows me to execute everything step, and here I can see my stack. You can see my stack here. So my stack is empty at the beginning. So let's ignore this, it's a technicality, and let's ignore this. And now I'm putting counter on the stack. So after this operation, my stack contains counter. And now I'm reading, now I'm calling my application global get, which gets my global, which will pop out the counter and get the value associated to counter, which is 3 in my stack. Now I put 1 on top. The stack is in the reverse order, so it's at the bottom, but yeah. And plus, it pops out the last 2 elements, add them. Okay, so now my stack contains 4. Now I store this element in my scratchpad 1. So you can see here my scratchpad. Now I have 4. Okay, now I put on my stack counter again. I put what I put in my scratchpad, which is 4. So now my stack will counter and 4. And now I call the global put, which is writing my global state. So it will write 4 the global state counter associated to the key counter. Okay, and to end, you just need to put 1 on the stack. So to end the program and be happy, you say you put 1 on the stack and you return. End of the story. So that's how things happen and how you can debug your smart contract. Yes. Yes. Okay, so it depends a bit on the blockchain. So on Algorand, you have the compiler will check for you the size and the smart contract. Anyway, Algorand will not allow you to deploy a smart contract with more than 8 kilobytes of size. So that's for the size. And now for the cost. So as you said, infinite loop and things like this. It depends on the blockchain. On Algorand, we'll see there is a maximum cost. So if you go around above this maximum cost, your smart contract is killed, like, and the transaction fails. On Ethereum, the cost, so on Algorand, the cost is essentially fixed. I mean, it's slightly more complex than that. But on Ethereum, the more you pay, the more you can run longer. But whatever happens, the story is that on all the blockchain, you have a limit, like, which is more or less defined by how much you pay, of how long your smart contract can run. And now there are 2 options. Either if you write your smart contract and it has an infinite loop, too bad. But actually, an infinite loop might not be the worst. Like, the worst is that if somebody can steal all the money out of your smart contract. So this is something that you need to verify. And that's, again, the $1 million question that nobody knows how to properly do. Okay, so on Algorand, the cost is I mean, on all, let's start. On all the blockchains, the cost is dynamic because it's possible that my smart contract is doing a loop of 10,000 loop if the state contains 10,000, and in a loop of 2 if the state contains 2. So the cost is not something fixed. It depends on the state of the blockchain. So on the smart, and usually what happens is that if you go above your maximum allowed cost, your transaction fails. And you need to evaluate properly the cost. On Ethereum, that's very simple. You need to evaluate properly the cost to give enough gas. Otherwise, you fail and you lose your gas. On Algorand, it's slightly simpler. If you do not, your smart contract will just fail if you are lower and you actually don't use your, there is no gas notion, so you don't use your fee. So it's slightly nicer, but still, I mean, it fails. And it's for you to evaluate. Like, I'm pretty sure you can use tool and you can do some evaluation yourself, but it's something that you need to do, and that's not something that may depend on the state. So it's not something that is the compiler can tell you the smart contract will use this amount of state cost, because it depends on the state. Now, this thing like this driver and I showed you, this debugger actually can compute exactly the cost in the current state of the blockchain if you were sending exactly at the time you run the debugger. So it would tell you how much cost it is. But nothing ensures that the state does not change between the time you run the debugger and the time you actually run your transaction. And if you have a bug in your smart contract, it's too bad for you. Okay, that was just a backup slide, but luckily I didn't have an issue with the demo. Okay, another thing that is useful to just know how it looks, like don't need to understand full detail, but to know how it looks is how jump works. So like in all this assembly type language, you don't really have like for loop, while loop, or anything like this. Like the only thing you have is a jump. And here, for example, this is a jump, this instruction, this opcode is a jump. If the previous value on the stack is non-zero, I jump here. And that's how we create a loop, because I put 0 on the top of the stack, then I put 1 and I add, so I get 1. I do something, then I put 10 on the stack. So now on my stacks, I have 1, 10, and I compare them. 1 is less than 10, so it's true, so it's non-zero. And so I loop and I continue until at the top of my stack, I have 11, and then I exit the loop, like I continue here. So that's how you do a loop in any assembly language, like whether it's TEAL, PyTEAL, as x86 assembly, whatever assembly language, it always look like this. And that's important to know that. It's important for your culture and important to recognize it if you debug. Okay. Slightly more advanced, again, more important if you, from your general culture, is like the notion that in any assembly, so there is a difference between like an assembly language and the bytecode. So TEAL is called an assembly language in general, in the sense that it's very, very low level. It's very similar to what the machine executes, but it's not exactly what the machine executes. Like the machine does not, if you think about in the case of your computer, the same way. There is an assembly for a computer, but the assembly is readable by a human person. The computer does not want to have to read push int larger or equal. The computer wants to read very simple thing, like very simple byte. So it reads more something like this. So in practice, what happens is that the lowest level a human can program, a real human can program nowadays, maybe in the very, very past, it was not like this, but nowadays, the very lowest level a human program is the assembly level, like using this opcode. And the way it works is that then you have a very simple program, compiler, assembler, that converts this opcode into like machine language bytecode, which are really, really dirty things that no human can understand. And usually in all these assembly language like TEAL, you have two types of opcode. Like a real opcode is really like, I have this, I convert it directly. And pseudo-opcode are more like, these are something that helps you. Like in the case of TEAL, you have like this int5, And actually, int5 is not something that exists in the bytecode. Int5 is first converted into a real opcode. Depending on many cases, it's converted into this or that. And this is what actually is then converted in bytecode and executed. Yeah. Okay, so just a bit advanced here, but just it's important. I mean, it's good. Okay, so now, so I've talked to you a bit with TEAL and kind of very low level language, but in practice for your homework, you won't need to do TEAL. You will code something in a much higher level language, Python. So in practice, what happens is that you write something in Python like this, and it spits out the TEAL script that is then compiled and sent to the blockchain. You have the documentation here. And let's now look a little bit more detail about how TEAL and PyTEAL can be used to do all the operations we discussed before. So remember, we said that smart contract allows you to read and write data on the blockchain in the state. It allows you to access the other function and so on and so forth. So we have seen how to read and write data on the blockchain. Let's see how now to access the other transaction in the group and access transaction properties. So for that, you have like 3 opcode. On the left is TEAL, on the right PyTEAL. So this is global, is the access to global parameter, like the size of the group, if you have an atomic group, the timestamp, like what time it is, actually what time it was the last block, and it's a bit approximate, but give you already an idea. Access to all the transaction properties. For example, you can know whether your transaction was a no-op operation, the default operation, or was an update operation, or this kind of thing, doing this on completion. And access to other transactions in the group. Like, remember the case where Alice wanted to give money to the application account and call the application at the same time, like so the application knows that Alice gave algos to the application account, or like a donator want to give money to the project, so then do an atomic transfer, an atomic group of 2 transactions, sending algo to the application account and calling the application. So to access, to check that the payment was done properly to the application account, you would access the transaction field of the payment fraction using GTXL. So let's see some example, more detail. So one thing that you will want to check in the specific case of Alice sending money as a donator to a project is that the transaction she's sending is a payment, because if she's actually doing an application call or something like this, too bad, like you want a payment. So in PyTEAL, it would look like this, GTX and 0, like the first transaction as type is equal to payment. And in TEAL, it looks like this. You put the type of the first transaction, you push on the top of the stack the type of the first transaction, and then you push the number that correspond to the payment, and you check if they are equal. Second thing is you want a bit orthogonal is to want to be able to check what kind of application transaction you are. Are you a no-ops, the default one, or are you doing the opt-in or this more advanced? So for example, in that case, you can check that you're a no-op using this equality in PyTEAL and that transfer like this in TEAL. Global variable. Let's suppose that you want that to say that the funding ends in February 1st. So the way you would do that is you would check that the latest timestamp is larger than the timestamp of February 1st. So I don't know if you know timestamp, but timestamp is just an integer representing a date. Like there is an integer that represents any date on Earth. It's called a Unix timestamp, and that's what we use here. There is a bit of a caveat that the latest timestamp is best effort and cannot be completely guaranteed because the blockchain has not access to the external world, so it does not know the time. So, but there is, like the block proposer can somehow indicate the time. It's a bit more advanced, but essentially you can do that. Short story, long story. Okay, so let's be very coming back to the example of Alice as a donator sending money to the application account and application calling the application. The way you would check that Alice paid, for example, 2 algos, is you check that the group is size 2, like that are at these 2 transactions, that the first transaction is a payment, paid payment, that the amount of the first action is 2 million because the base unit in Algorand is a micro algo, so you need to multiply everything by 1 million, so it's 2 million for 2 algo, and that the receiver is the application account. That looks like this in the TEAL. So what I did not mention is this assert. So assert says fail if this condition is not true. Stop the smart contract, fail it if it's not. Just for those who really want to be clean, this way of doing is not actually the clean way. And okay, I don't want to elaborate, but you can read the slide later. Okay. Now, how do you issue transaction? So the last thing that we need, so we saw read-write states. We saw a lot of basic operation, comparison, addition. We saw receiving token. Now we need to see how to send token from a smart contract. The last important thing to do from a smart contract, sending token out of a smart contract. And to do that, you use inner transaction. And in PyTeal, it looks like this. You say, I start an inner transaction. I say my inner transaction is a payment of this amount of this receiver, and now I submit it. There are some constraints, and here that come back to the first slide, the first technical slide, which says like you have an application, you have an account array in the transaction. So you need the account array to contain the right thing, but that's just a technicality. But essentially what you want to do is just this. And then the attributed form is actually very simple. It's you can read it, it's read very simply. And at the end of the day, when this is executed, then a payment of 1.42 algo is sent from the transaction from the application account to the caller, the sender of the application call. This means that the caller of the application. I don't know why. Yeah, that's the application call, but application caller. Okay. Last technical, almost last technical thing, the subroutine. So I'm sure that you have learned that when you code, you need to write function. I'm sure that you are not using them as often as you should, but you should never copy paste code. That's bad. And I hate when people copy paste code because that's where things start to go very badly, very quickly. And every time you have some code, you need to organize them properly, modularly into function and really avoid absolutely copy paste. And that's the same in TEAL. You don't want to copy paste bits of PyTeal or bits of TEAL. And so to avoid that, you use what's called subroutines. So it's really internal function. And the same way you would use function in normal programming language, you would use TEAL subroutines. Very important to be clean and use as much as relevant. So the way you do it is that you need to add this decorator, and I will show you in the next slide why you need to add this decorator to say it's a subroutine. And it's used to improve the code quality and to reduce the code size, because now the subroutine function, like the subroutine content, the function subroutine is not copy pasted 10 times in the TEAL. It's not in the resulting TEAL code. And so your code is shorter, much better. Importantly, it's important to understand that these function subroutines are not visible from the outside. You cannot say, I make an application call calling this subroutine. Like these subroutines are really just for you to improve your code quality and reduce code size. It's not to be called. And just what I promised you about the decorator, if you write the decorator, you actually create a subroutine. And if you know a bit about assembly, it's very similar to most assembly you would know, where you would actually be able to call the subroutine and then return to the subroutine. And you see in this TEAL program that the modulo operation is only written once, and then the 2 times we call the subroutine that does the modulo operation, it's just like 2 times we call subroutine. There is no modulo operation here. Like it's really, there is 1 time the code with the modulo operation and then just call. This is the proper way. If you forget the decorator, then what's happening is that PyTeal will think that you want to copy paste the code. So there might be a reason in which you want to copy paste the code if the code is very short or it's used only once. But in general, that's not what you want to do, because you can see here the code is copy pasted twice. But maybe you see in this case, maybe it's good because it's slightly shorter. So depends. So, but in general, you still want the right. Okay. Now, last part related to subroutine. Subroutine cannot be called directly. But how do you call a smart contract on a specific action? How do you say, I want my smart contract to do a specific action, to record that I donated this amount of money or to reimburse me? The way you do it is to use the application argument. So every application transaction have this application call transaction, have this application argument as part of it. And usually you need a convention here. Like it's not like you can do whatever you want, but in life you need convention so that it's not a mess. And currently the convention is to say the first argument is a method name. So the first argument in your application transaction call, application call transaction, it would be the name, like for example, funding or withdrawing or reimbursing. And very soon, but it won't be for your class, you will need to follow the ABIs that give a bit more advanced rules that are more better suited actually. But for you, just think the first argument is the method you want to call on your smart contract, what you want to do, the action you want to make. So now that we have seen all of that, let's see what a smart contract looks like. Like this is kind of the basic skeleton. So essentially, the main thing is that you have a big test. So the code is like a switch. Like if you know most languages, it says it's a switch. So if this holds, then do that. 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 So it says if the application ID is 0, this means that we are creating, then I do on creation. If the application on completion is delete application, so this call will at the end of the call delete the application. Here, what I decided to say, return is creator. So only the creator of the application is allowed to destroy the application. If I'm not the creator, if the sender of the transaction is not the creator of the application, then it will return false. This means fail. So that prevents anybody else from modifying. In a hardcore DeFi application, here it should be return 0 because hardcore DeFi application thinks that code is low and there is no right to update. So in that case, you just would say deleting and updating is forbidden, return 0. But in non-hardcore application, maybe you want to allow the creator to modify it, okay? In case there is a bug. And like, okay, for example, you can test if it's close out, opt-in, and then you can check that where it checks the method. So if you call the method vote, then do the on vote. And maybe you will have a method withdraw or whatever else you want. And they would all be added here. So in your voting application, the skeleton would essentially look like this, and you would just need to massage it a little bit to do what you want. This is the skeleton before the ABI is finalized, but that doesn't really apply to you. You can forget about this. Okay. Okay, so let me show you a simple example, okay, of an application. So it's a very, oh no. So this is a very, very, very simple example application. The only thing it does is that if we call the method pay me, it sends you 0.2 algo. So anybody who calls the method pay me of this smart contract gets 0.2 algo. So it's a very useless smart contract, but just illustrate a bit what's happening. So this is the main program. So at creation, I just approve. I don't do anything. Deleting the application, I only the creator allows the creator to delete it. And in case of no op, I handle no op. So here I did slightly differently. And in the no op, I check that I'm calling the method pay me. So if the method is not pay me, I fail because I have only one method in this smart contract. It's very simple. And if the method is pay me, then I create an inner transaction of payment of 0.21 algo to the sender. Like that's very simple. And something I did not talk about, but you can on Algorand and in many languages, many blockchain, you can also log things to the outside, which is useful for debugging, and it's useful also for external application to know what's happening. So here we also log the information sent 0.21 algo. Okay, so now let's look how we execute it. So here, last time I did everything using bash script. That's one option. The other option to execute smart contract is actually what you will most likely need to do is using Python or JavaScript and the SDK. And here I'm using Python. I prefer Python. So the code in Python first gets the account. So you can just some detail here. And then I just print on the console the account. Oh, I'm not sure I will be able to. Oh, I see. I print the address of the two accounts that I'm using for this demo. So this is like just technical function. And now I create the application. So this is a bit of a complex function, so I don't show you how it works. I mean, it's not that difficult, but just for the sake of this demo. This is ready. This sends the transaction. Oh, yeah. And it says the transaction is confirmed. Now I can get the application ID, the application account. Okay, and let's go. Now it's time to play. So at the beginning, my application account is empty. So obviously the smart contract cannot do anything because the only thing you can do is pay out of the application account. If it's empty, it's empty. Too bad. So the first thing I need to do is to fund the application account. So let's first check that it's empty. So it's empty, balance is 0. And then I make a payment transaction from Alice account, this is Alice account, to the application account of one algo. 1 million is one algo. Okay, so I'm doing it. Then I need to sign it. It's Alice account. I need to sign it. Luckily, I have the private key of Alice. And I need to send the transaction. Okay, the transaction is confirmed. Now, let's see what Bob is. Okay, it doesn't matter too much, but now I see that my application account has one algo. And Bob, I just print Bob amount because I will need to show you how it evolves. Because what I'm doing now is that I will make Bob call the smart contract with the pay me so that we should receive 0.21 algo. So let me do this. So, okay, so I'm finishing this. I'm just finishing showing you this demo. So here I'm creating the application transaction from Bob to the application and saying pay me, like with the argument pay me. I'm signing it by using Bob's private key. This is just to be able to debug, but you don't care right now. I don't have time to show you. And I send the transaction. And now I print the balances, and you see that my balances have updated. Wait. Okay. You need to scroll down. My balances of the application account decreased by 0.21 algo, and this one increased by 0.21 algo. Okay, now I'm deleting the application because I don't care about it anymore. Yeah, I think, yeah, that will do it. Okay.